session. Our first talk in this session is Lorenzo Ruffoni, who will be telling us about graphical splittings of Artin kernels. So take it away, Lorenzo.
Thanks everyone for being here, and thank you to the organizers for the opportunity to present some of my work at this conference. Very happy to be here. So my talk today is going to be on the geometric group theory side of this conference. I'm going to be talking about right-angled Artin groups and some of the other subgroups. This is joint work with Miguel Barquinero and K. If you have any questions at any time, feel free to just interrupt me or write in the chat. I have that on my side screen, so I should be able to see that. All right, so here we go. I'm going to start off just with definitions. These groups are very easy to define, so I hope that definition is going to be understandable. So these are groups defined by a finite graph. So that's my starting point, just a bunch of vertices and edges. And I'm going to associate a group to that in the following way. I take all the vertices as generators for my group, and then I make two generators commute if and only if the corresponding vertices are connected by an edge. So these are groups in which the only thing that can happen is that some variables commute. That is really the only relation that you have. Examples are over here. If I start with a totally disconnected graph like the one on the left, I have here 5 vertices. I generate a group which is a free group of rank 5, just one generator for each vertex, and nobody's commuting with anybody. And the opposite side, if I take a complete graph like the one on the right, I have 5 generators and everyone commutes with everyone. So this is a free abelian group Z to the 5. Everybody's commutative here. And in general, right-angled Artin groups, or RAAGs for short, are somewhere in between those two extremes. So free group and free abelian groups are classical examples of RAAGs. And then whatever in between where you impose or drop some commutators is also a RAAG. One of the biggest features of the theory, I mean, the reason why I really like the theory of RAAGs is that the algebraic properties of the group can often be detected just by looking at the graph. So there's a fruitful interplay between the geometry of the graph and the algebra of the group. Just to give an example, on this middle graph over here, this is a bipartite graph. You can see there's like a group of vertices over here that are not connected. So that gives you an F2, that's your F2 subgroup. Over here, you see a collection of 3 vertices that are not connected to each other, is completely disconnected. That gives you your F3 subgroup. And then everything from the F2 is connected to everything from the F3. And so that gives you direct product decomposition. Everybody from one side commutes with everybody else from the other side. So you can see how the bipartite structure of the graph is reflected in the algebraic structure of the direct product. So these are the type of groups that are kind of the ambient for what I'm going to be talking about. And specifically, I will be talking about some subgroups, which we call Artin kernels, which are obtained in the following way. I start with my right-angled Artin group. So this is my RAAG. And I consider a map to the integers. So a way to define that is just to take any vertex in the graph and then associate that to some integer number. Okay, so just take your graph and label the vertices with integer numbers. That defines for you a group homomorphism to Z, and I'm going to take the kernel. The kernel of that is what I call an Artin kernel. And then the question is, can we understand what kind of groups we create in this way? And just before going into more definitions and examples, I want to say what kind of results we obtain about them. And this is my box over here. So results we obtain about Artin kernels and about splitting these groups, understanding them, and how can we decompose them into easier groups. Find formulas for the rank of these groups. If you're not familiar with what the rank of a group is, that's just a measure of its dimension, how big the group is, and then find some exotic behavior that we can find with these Artin kernels. So these are the 3 results that we present. Let me start by saying why maybe you might be interested in Artin kernels coming from different backgrounds. So in this slide, I just have examples of groups that arise as Artin kernels, or happen to be Artin kernels, I should say. Well, the first case is the abelian case, and I'm sure everybody has played around with free abelian groups in their life at some point. So this is the case in which the graph is a complete graph. The RAAG is just a free abelian group of rank n. And then if you take any map from Zn to Z, say, non-trivial map, this just boils down to linear algebra. So your kernel is just going to be a codimension 1 subgroup. Just the rank of the group drops by 1, and there's not much to say here. Second case from three-manifold topology. So here, this is the case in which gamma is a tree, so not very connected. There are not many edges around. It's a theorem of drums from the 80s that in this case, the right-angled Artin group is the fundamental group of a compact three-manifold. What kind of manifold you get? I'm going to drag your attention to the right-hand side. The kind of three manifolds you obtain in this way are mapping tori for surface diffeomorphisms. So here the construction is you start with a surface, and the surface is going to be non-compact. I mean, compact but not closed. Let's say compact surface but not closed. So there are some boundary components. You take a diffeomorphism of the surface, and then you glue the surface back to itself using the diffeomorphism. So that's the kind of three manifold that you get from here. From the very description of the manifold, you can tell that these groups will be free bicyclic, where the free subgroup is coming from the fundamental group of the surface, and the cyclic part is coming from the mapping torus construction. So this diffeomorphism that you use for the gluing. It's a classical theorem by Stallings that if you have a compact three manifold and the fundamental group has a surjection to Z with finitely generated kernel, then that is induced by a fibration of the three manifold. So the three manifold is a mapping torus obtained in this way. So from this point of view, the bottom line is that if you're looking at compact three manifolds, looking at maps to Z with finitely generated kernel is the same thing as saying that the manifold fibers over the circle, and you're studying in how many different ways the fibration can be arranged. Okay, so from the theory of three manifolds, it's like a huge collection of examples of Artin kernels. Here, the kernel always happens to be a free group. So there's not much to say about what kind of group you get. The only information is about the rank of this free group. And you can see here what kind of bound is available. Last example is more algebraic or algebra topological, and this is due to Bestvin and Brady. This is the case in which the graph can potentially be whatever, but the map to Z that you're taking is the one that takes every vertex to 1. Okay, so if you remember from my previous slide, I was saying that this homomorphism to Z can be defined just by labeling the vertices of the graph. And what I'm saying here is that we're looking at the labeling that is 1 on each vertex. So the simplest thing that you can possibly do. What they proved in this case is that the finiteness properties of the kernel can be detected by the graph, the topological properties of the graph. So for instance, they proved that the kernel is finitely generated if and only if the graph is connected, and that the kernel is finitely presented if and only if the Flood complex generated by the graph is simply connected. So again, this is another class of groups that happen to be Artin kernels due to Bestvin and Brady. And in my talk, I'm going to be considering general Artin kernels, so given by any possible map from the vertices to Z and from various classes of graphs. The main tool for us has been the study of the leaving subgraphs. So in general, if you start with a connected graph and you take any map to Z, the first question you want to answer is, when is the kernel finitely generated as a group? And we had this result from the 90s, Meyer and Van Wyk, that gives a criterion in terms of what they call the leaving subgraph. And they say that a kernel of F, your Artin kernel, is finitely generated if and only if a certain thing, which is called the leaving subgraph, is connected and dominating. So before going into the definition, let me just bring your attention to the right and just draw what the leaving subgraph is on the right in these examples. So leaving subgraph is what you get if you look at all the vertices which are not sent to 0. So for instance, in the first picture, I'm just going to forget about the vertices that go to 0. And if you see a pound symbol, that means send this vertex to whatever number you want, integer number, as long as it is not 0. So these are the vertices that don't go to 0. And I'm going to connect them because they're connected in the graph. So that's the leaving subgraph here. In my second example, this is the collection of vertices that do not go to 0. And I'm going to connect them because they're connected in the graph. Same for the last example. Okay, so in yellow, I'm highlighting what the leaving subgraph is in each case. Well, their condition is that the Artin kernel defined by those numbers is finitely generated if and only if this subgraph is connected. Well, I guess we know what connected means, and dominating. Dominating means that it has to be large enough to cover almost the entire graph. So dominating means for any vertex in the vertex set, the distance between the vertex and the leading subgraph has to be at most 1. Okay, so for instance, the first leading subgraph does not cover these 3 vertices, but they are distance 1 from the yellow graph. Same for the last graph. The last graph does not cover these 4 vertices, but they are all at distance 1 from the yellow subgraph. In the second case, these points are not covered, but they are at distance 1 from the leading subgraph. But you have 1 point over here, which is too far away from the leading subgraph, so that's not dominating. Okay, so that's their gadget. Do this kind of construction on any graph, and you know if the kernel is finitely generated or not. And then our question was, all right, can we understand a bit better why things are finitely generated or not? And when they're finitely generated, what kind of group is that? Can we decompose this group into some finite description and see what is going on? So this is what we've done, for instance, in the class of chordal graphs. Definition of chordal graph is that every cycle must have a chord. So if you look at the right, my first graph is not chordal because over here I have a 4th cycle which does not have a chord, or diagonal if you prefer. So this is not chordal. If you draw a diagonal, you make it chordal, like the second and third graph, they're equal and they're chordal graphs. Example to keep in mind is the case in which gamma is a tree. A tree has no cycle, so of course is a chordal graph. And back to one of my first slides, this is a kind of 3-manifold topology generated. And in this case, the RAAG is 3-bicyclic. And all I'm going to say today was covered in this case by Cashin and Levitt in a paper by 2016. But here's what we prove for more general chordal graphs. You have a dichotomy in the behavior. We know the kernel can be finitely generated or not, and we specify those behaviors a bit better. So in the case you are not finitely generated, which we call wild, the kernel actually surjects to a non-finitely generated free group, F infinity. So it's very much not finitely generated. In the case you are finitely generated, which we call tame, you can actually decompose the group and find that it is what people call a generalized Baums-like-Solitor group of variable rank, which is like a long fancy name to say that your group is a graph of groups with finitely generated free abelian groups at the vertices. So just to unpack all these words, if you look at my graphs on the right, the second and the third, you can kind of see that those graphs are obtained by gluing together complete graphs along complete subgraphs. Like you can see here, for the second one, there's a triangle here glued to a triangle here along an edge, and then there's another triangle glued along an edge, and then there's an edge glued along a point, and so on. It's just a bunch of complete graphs glued together in a certain way. And on each complete graph, the Artin kernel looks like z to a power, a free abelian group of finite rank. And then what I'm saying in the statement is that we can see that those blocks are actually the only responsible for the structure of the Artin kernel. So from the structure of the group and the numbers, we can compute how to glue together free abelian groups to reconstruct the entire Artin kernel. This becomes explicit, especially in the case of block graphs, which is on my next slide. So block graphs are a class of chordal graphs, a bit more restricted. Here, these graphs are obtained by gluing together complete graphs, just meeting at vertices. So for instance, the first one is chordal, but it is not block, because here I'm gluing those 2 triangles, which are complete graphs, not along an edge, but not along a vertex, but along an edge. So this is chordal, but not block. The second and third graphs are block graphs. So you see that's like a complete graph on 5 points attached to a bunch of edges. So these are the kinds of graphs I'm looking at here. Again, keep in mind the case of the tree. Tree is a case in which you're gluing together edges at points without creating cycles. So that's certainly a block graph. And again, this result was covered by previous work of Cashin and Levitt. So to apply our previous theorem to this situation and re-understanding what the various building blocks look like, we can actually compute the kernel of the rank. So here in this statement, I have a block graph and I have a map to Z. The condition is that this map should be non-zero on the cut vertices. That is to make sure that the kernel is finitely generated, so it makes sense to compute the rank. And then we have this formula here that I don't really care about reading the formula. Let me just highlight what the contributions are. Well, you have the first summation is over blocks, and blocks are complete subgraphs in your graph. So here you see there's a summation over things that depend on B. So each block gives you a certain contribution depending on how big it is and what the function does on that. The second summation is a summation on vertices. And given how this is written, this is actually a summation over cut points. So the bottom line, the only thing I want to emphasize here is that in this formula, you can compute the rank just knowing what your graph looks like, especially what the complete subgraphs are and what the articulation points or cut points are, and what the value of f is on those. Just write it down, and this is very explicit. You can compute the rank. So we use this explicit formula to do some exploration of the space of fibration of a right-angled Artin group, which means coming from three-manifold topology, how many different ways can you fiber a three-manifold over S1? Here we're asking how many different ways can you fiber a RAAG over Z. And one thing we can compute is, for instance, the minimal rank of a fibration of a kernel. You can see on the right-hand side, this is an example of a character that realizes that minimal rank. So you send the cut points to 1, and you send the non-cut points to whatever you want. That is a fibration of minimal rank. We can also construct fibrations whose kernel has larger and larger and larger rank. So for instance, the bottom example in my slide, you send the cut points to n and everything else to 1. You apply the formula, you find that the rank is growing linearly in n. So as you increase n, this is going to blow up to infinity through a sequence of Artin kernels that become larger and larger and larger. And then the last phenomenon we found, I'm going to take this one to the next slide, is what we call bounded divergence. And it's the following phenomenon here. A sequence of characters, fn, from your RAAG to Z, with the following properties. For each fixed n, the Artin kernel generated by that is tame and constant, meaning that it is a finitely generated group. The rank is always the same, independent of n. And it's actually the same as, in terms of this graph of groups, the composition is always the same group. But in the limit, you get something which is wild, meaning it surjects to f infinity. So very large. Concrete example on the right, I'm sending the cut points to 3, and everything else, I'm sending that to some power of a coprime number. You apply your rank formula here, and you find that independently of n, the rank is always a fixed number. But when n goes to infinity, that labeling converges to the labeling down here. And I'm not going crazy. I'm not saying that 3 converges to 0 when n goes to infinity. I need you to understand this up to a scaling. So 3 over 2 to the n. Okay, I'm normalizing everything by 2 to the n and so on. So of course, 2 over 2 to the n that converges to 1, 3 over 2 to the n that converges to 0. So this limit is something you want to understand projectively. So up to rescaling the characters, which is not a problem. Like if you have a character and you look at the kernel, you rescale the character, the kernel is always the same. It's defining the same subgroup for you. So that's not a problem if you're interested in the kernel and not in the function itself. So you can formalize that by looking at projective first homology or the so-called BNS invariant of your right-angled Artin group. And what this is saying is that the rank function is not a proper function on these spaces. All right, so this is what we found. Thank you so much for your attention.
Let's thank Lorenzo. Any questions? Please feel free to unmute yourself or type them in the chat.